What specific problem does the proposed PLADIS method aim to solve in the context of diffusion models, and how does it compare with existing guidance sampling techniques?
The proposed PLADIS method aims to solve the problem of enhancing the performance of diffusion models without requiring additional training or neural function evaluations, NFEs, which are common limitations in existing guidance sampling techniques. Unlike methods such as classifier-free guidance and autoguidance, which rely on additional training or poorly trained models, PLADIS substitutes cross-attention in diffusion models with adjusted attention mechanisms that emphasize sparsity, specifically using the alpha-text and max operator. This approach not only improves sample quality and text-image alignment, but also maintains compatibility with other guidance methods and guidance-distilled models. Furthermore, PLADIS circumvents the need for specific layer identification and reduces computational costs associated with NFEs, making it a more efficient and effective solution compared to existing techniques. Overall, PLADIS leverages the advantages of sparse attention to achieve significant performance improvements in text-to-image generation tasks.
How does the proposed PLADIS method work? Please illustrate step-by-step the modification process involving the sparse cross-attention mechanism and its relationship with the parameters $alpha$ and $lambda$.
The proposed PLADIS method enhances text-to-image diffusion models by substituting the standard cross-attention mechanism with a sparse counterpart using the alpha-text and max operator. The modification process begins by replacing the dense cross-attention layers with sparse ones, where the parameter alpha controls the degree of sparsity. Specifically, values greater than 1 lead to increasingly sparse attention outputs. In PLADIS, the scale parameter lambda is introduced to adjust the influence of sparse attention relative to dense attention during the denoising process. When lambda equals 0, the model behaves like the baseline, while lambda equals 1 corresponds to the model with the sparse attention effects fully realized. By setting lambda to values greater than 1, PLADIS accentuates the benefits of sparse attention, leading to improved generation quality and text-image alignment without requiring additional neural function evaluations, NFEs. This method effectively leverages the noise robustness of sparse attention, as demonstrated by the performance improvements observed in various experiments.
Can you provide a simple example of how PLADIS improves the image generation process in comparison to traditional methods? Walk through the steps involved, including the effect of different $alpha$ values on performance.
PLADIS enhances the image generation process by substituting traditional cross-attention mechanisms with sparse attention using the alpha-text and max operator. For instance, when generating images with a standard model using softmax, where alpha equals 1, the model produces dense alignments that may not accurately reflect the relationships between text prompts and image features. In contrast, by increasing alpha to values greater than 1, such as 1, 5, or 2, PLADIS introduces sparsity in the attention mechanism, which leads to stricter matches between image and text embeddings. This adjustment results in improved generation quality and better text alignment, as evidenced by experiments showing that higher alpha values consistently enhance performance across various metrics. Specifically, with alpha equals 2, PLADIS achieves the best performance in terms of FID and clip score, demonstrating its effectiveness in generating more coherent and visually appealing images compared to traditional methods.
What are the theoretical advantages or practical benefits of using the PLADIS method compared to previous sampling methods in diffusion models, such as classifier-free guidance or weak models?
The PLADIS method offers several theoretical advantages and practical benefits over previous sampling methods like classifier-free guidance and weak models. Firstly, PLADIS does not require additional training or neural function evaluations, NFEs, which are necessary for methods like classifier-free guidance and weak models, thus streamlining the sampling process. Secondly, It enhances text-image alignment and overall generation performance by substituting cross-attention with adjusted sparse attention mechanisms, which improves noise robustness and reduces retrieval errors compared to dense attention. Additionally, PLADIS can be seamlessly integrated with other guidance methods, allowing for a more flexible and effective approach without the need for specific layer identification or increased computational costs. Finally, extensive experiments demonstrate that PLADIS significantly improves sample quality and human preference evaluations across various benchmark datasets, showcasing its practical effectiveness in enhancing diffusion models.
How was PLADIS validated or tested during experiments? Please describe the datasets used, the metrics applied, and how the results demonstrate the method's effectiveness.
PLADIS was validated through extensive experiments using the MS-COCO validation dataset, where 30,000 samples were generated to assess its performance. Various evaluation metrics were employed, including Frechet inception distance, FID for visual quality, clip score for text-image alignment, and human preference score, HPS version 2. 1. To gauge user preference. The results indicated that PLADIS significantly enhanced visual quality, text alignment, and user preference across all metrics when compared to baseline models, demonstrating its effectiveness. Additionally, PLADIS was tested in conjunction with other guidance sampling techniques, showing improved performance and coherence in generated outputs. The method's robustness was further validated through a user preference study, where evaluators consistently favored outputs generated with PLADIS over those without it.
What specific results were achieved with the PLADIS method in terms of image quality and text-image alignment, and what metrics were used to evaluate these improvements?
The PLADIS method significantly enhanced image quality and text-image alignment, as evidenced by various evaluation metrics. Specifically, it improved the Frechet inception distance, FID, clip score, image reward, and human preference score, HPS version 2. 1. Across multiple datasets including MS-COCO. The results indicated that PLADIS consistently delivered substantial performance gains, particularly in visual quality and prompt alignment, outperforming models without PLADIS in user preference studies. Additionally, the integration of PLADIS with different guidance sampling techniques resulted in more visually appealing outputs and improved coherence between images and text prompts. Overall, the empirical findings demonstrated that PLADIS effectively leveraged sparse attention to enhance the generative capabilities of diffusion models.